connection. And the previous milestone told us that it was possible. To confirm that, we did a Frist equation theory. The Frist equation does link budgeting, and what we did was kind of in reverse. We found out with the specifications of our card what the range of our system would be. The Frist equation is that top equation up there. It uses power, gain, the wavelength of your frequency, and the separation between two antennas. The most important things here were the power at the receive antenna, which is the minimum power required to be there, and the transmit power. The gain was the gain of our two antennas, which is the same on both, and the lambda was the wavelength of our signal. Here, range, we solved for range, and we put our data in that we had on the specification sheets, and we solved for the range. It told us that theoretically in a free space situation we'd be able to transmit at 102 miles. This is far beyond what we wanted, but this is in a perfect ideal situation, and here on Earth everything isn't perfect and ideal, and our attenuation tests told us that this was likely going to be possible to transmit at 5.7 miles.
Something that we have to take into consideration is the scalloping phenomena. Scalloping phenomena for our project was a big thing. Especially, I want to give a quick example for scalloping. Scalloping, let's say that you have a transmitter, a receiver, or an object in air and space. You have a transmitter, which in this case we're trying to use isotropic signaling. But isotropic, basically, realistically, it's not possible. Theoretically, it is. In this case, isotropic means that you're going to have intense signaling device in regardless of direction. So you're going to be transmitting in every direction, no matter what, at the same intensity. So in this case, let's say that you have a boat that's transmitting a certain height from the ground. In this case, let's say 30 feet from the ground, and you have an airplane flying in the air. The airplane is going to be an object. This is a transmitter. Transmitter is going to send waves through space. It's going to transmit waves through space. And you're going to have ones that are going to go directly to the object. Once it catches the object, those waves are going to bounce back to the transmitter, and it's going to, act as a radar to tell you, okay, this is the location of a certain object. Well, this boat, at the same time, it's because it's transmitted isotropically, there's some waves that they're pointing down to the medium. In this case, it's the water. These waves are going to bounce from the water as well, and they're going to catch with the object. And by catching with the object, they're going to refract back to the transmitter. So what's going to cause in this situation? You're going to have constructive and destructive interference. So what's going to happen is either going to add or it's going to destroy the amplitude of the signal. So you're going to have what is called scalloping signal, scalloping phenomenon here, where you're going to have certain areas in this chart right here shows certain areas where you're going to have communication link, and there's going to be other areas where there's going to be communication because it's going to be destructive interference.